In this module, I'm going to walk you through a Gaussian dispersion model that is used to model air pollution transport downwind of a stationary source. There are two examples in your textbook I'd like to point you to. You should be able to work these in your textbook. The first is, it has been estimated that the emission of sulfur dioxide from a coal-fired power plant is 1656.2 grams per second. At 3 kilometers downwind on an overcast summer afternoon, what is the centerline concentration of SO2 if the wind speed is 4.5 meters per second? And parameters are given for stack and for the atmosphere. If you perform this, you'll start by finding the stability class. And in this case, the word overcast tells you that you're going to have a stability class of D, because any overcast day is given the stability class D. The second thing you will do is find the effective height, or the effective stack height. This is the physical stack height. So the effective stack height is equal to the physical stack height plus the rise of the plume, and the rise of the plume is equal to the velocity times the diameter divided by the wind speed, 1.5 plus 2.68 times 10 to the negative 2 times pressure times Ts minus Ta divided by Ts times D. And if you plug in all of the things that are given, you should have a change of H equal to 8.0 meters. And so the effective stack height is equal to the 120.0 meters plus the 8.0 meters you solved for, 128 meters. The third thing that you will do is find S of y and S of z. You'll use the relationship of S of y equals A times x to the 0.894, and S of z equals C times x to a D coefficient plus F. You'll use this table to find that. So in this situation, we're looking at stability class D. And it was given that we're looking at a location 3 kilometers downwind, which is greater than 1. So we're going to use these coefficients in the problem. And if you substitute those in, you should be able to find 181.6 meters and 65.4 meters. The fourth thing that you'll do is use the long form of the equation, because no inversion is present, to solve for x. And so that equation is E divided by pi S of y S of z mu to the exponent negative 1/2 y S of y squared. So I encourage you to try to punch in all of the numbers to make sure you know how to work the calculator for this long problem. And the answer you should get at the end of this is 1.5 times 10 to the negative 3 grams per meter cubed. The second example I'd like for you to try to perform is this one. The problem statement says, determine the distance downwind from a stack at which we must switch to the inversion form of the dispersion model given the following meteorological situation. So the first step will be to determine the stability class. In this one, it stated that it's no cloud cover, that you're in the summer, and you're during the day, 11:30 a.m. And so if you go to that table, in this situation, we have day, no cloud cover in the summer, probably a strong solar radiation, but the wind speed that's given was 7.3 meters per second. So you'll choose stability class C. The second thing that you'll do is solve for S of z with an inversion, 0.47 L minus H, and you should get 141 meters. L here is 350 meters, and the effective stack height is given. The third thing you'll do is use the plot to find x of L at this S of z. And when you do that, you should find an x of L of about 2.5 kilometers. So the fourth thing is just to recognize that 2xl is around 5.0 kilometers, and at a distance at an x greater than 5 kilometers, you'll use the inversion form of x equation. So that is what was asked in this question. At what distance downwind would you use the inversion form of the model? So again, I encourage you to work through these examples, and that will help you perform the class exercises.